Okay. So we're moving through our different integration techniques here. We have one more after this, but F5 kind of stands on its own, and we won't even be talking about that until next week. But we've sort of looked at a couple different things there. We started out with U substitution because that's what you should always check for first. A lot of times you can get yourself in the weeds trying to do this, that, the other thing, when it turns out you could have just done a U sub to get your answer. So that's part one of it. The remaining things we looked at all dealt with quotients. If you had an improper rational expression, you just used long division and you were done, right? So that's where we started. So if that numerator power is equal to or higher than the denominator, you're going to do long division. And then the next two we looked at, which were completing the square and partial fractions, those ones look the same. As a matter of fact, yesterday online, like we had two examples where the only difference between the two were the denominator ended in plus 10 in one and it ended in plus 8 with the other one. And that's because when you complete the square, you need to have that the constant number that you have after your completed square be positive in order to match an inverse trig derivative. The two inverse trig derivatives that we're really going to see are arctangent and arcsine. Arctangent doesn't have the square root. That's the one that we'll see. It'll either be an arctangent or it'll be a partial fractions. If it's a sine one, you shouldn't get a negative in the bottom because we're never going to learn the technique that you would do if you got a negative in the bottom. That's the trig substitution technique, which is not part of the BC curriculum. So we won't know how to do those ones. So that means, anytime you have that square root in your denominator and you complete the square, everything should work out for you. Integration by parts, this is a big one. This is I think the most, it's the one. It's this is the technique that kind of does the most work for us. The nice part about this is it's not quotients. So if you have something that isn't a quotient and U sub doesn't work, then this is your go-to on it, integration by parts. And it really is just a play on the power rule. So we're going to take, it's not necessarily reversing the power rule, because it's not exactly doing that. If you were reversing the power rule, you'd always have to have a sum of two things. You know what I mean? Because the power rule gives you the sum of two things. But it's almost like you have one of those two pieces of the sum. That's kind of what's happening. You have one of those two pieces in the sum that you get from a power rule, and that's actually enough to integrate it. So we have the power rule that we all know and love, the derivative of two functions u, v, being multiplied by each other, which look like the same letter when you write them out by hand, u and v, for added confusion. But the derivative of u, v is the derivative of the first times the second plus the first times the derivative of the second. What we're going to do is we're going to integrate both sides of that. So I'm just going to write the integral of d dx uv, which equals the integral of u prime v plus uv prime. There is no dx there because that dx is kind of baked into the primes. Okay, so there's no dx written there because it's baked into the primes, and the dx is kind of baked into the fact that we've taken the derivative of uv. So that is good math. That is correctly written. What's the integral of the derivative of uv? It's uv, right?
How do we know then that for the second part of it that we're integrating uv?
Oh, because we don't, because I didn't write it. Yeah, I agree. This should say plus integral. Yep. Good point. Yeah, I had no idea what you were asking, and then I realized what I had written. Yes. No, so yeah, we definitely absolutely want to do that term by term to show. You're right, because usually we use the dx to show when the integration ends, and without the dx, it wasn't there, but that's why I would want to write it as two separate integrals. So this is uv, and these I'm going to actually leave as is, because in a second we're going to have the integration by parts formula. uv prime. all I'm going to do, because if you look at the beginning of the integration by parts formula, which I have in a slightly different notation on the board, I've got u and I've got v prime. I'm just going to solve for it. So I'm going to solve for u v prime, which is my integral on the right. And then I'm just going to, I guess I'll solve for it this way. I'll bring this over to the left, and then I'll switch sides. So this, the integral of u v prime, equals uv minus the integral of u prime v. So what's going to happen here is we're going to sort of do a switch, right? We're going to kind of have where we had u to begin with, our new integral is going to have u's derivative. Where we had v prime to begin with, our new integral is going to have v's antiderivative in it. So yeah. I didn't write a plus c anywhere because I have an integral on both sides. So we are good to not write that plus c anywhere, because when I integrated this, I would put a plus c. When I integrated that, I would put a plus c. Even in this line, I'm still good to not have a plus c here, because these guys would get their own plus c's. And since that could be any number in the world, having that uncertainty is good enough to, you would be able to get uv from that. You just have to pick the right c. So we're good to write all of those. Those are all good notations, if you care. Okay, so that was with the prime notation. You could, two ways of writing it. Everywhere where I had v prime, we're going to use this more often, the dv's and the du's. So let's jump right into it. The first part about this, because any good integration technique, involves you having to pick something and pick it correctly, right? We have to pick our u. When you've got to pick your u, and then the rest of the integral is going to be your v prime or your dv. dv should be the more complicated part of the integral that can be easily integrated. I read that and I feel like that's almost like saying two opposite things, because usually the more complicated it is, the harder it is to integrate. But it's really u that you're looking for first. These aren't my notes. So really looking at number 2, u should be the part of the integrand whose derivative du is simpler. So we want u to get simpler as we go along. And it turns out, and there is definitely, this is a guideline, this is not perfect. I could probably find, if I looked hard enough, an integral that would make this untrue in every single case. But this is a good, especially for a simple practice problem, one that you're just learning. This will tell you, kind of what to look for to pick your u. If you have something like ln, that's usually what we pick first as our u. If we don't, but we have inverse trig, that's what we're going to go next. Algebraic means x squared, x to the third power. Trig, and then I actually don't know if I've ever seen one where it has been an exponential that you've picked, because it's like the last thing. What the heck else do you have in your integral that isn't in this list, I guess is what I'm kind of saying. So this is kind of LIATE. This is kind of a guideline that might help you, but in most cases will help you pick out which to choose for your u. And then in most cases, you only have 2 choices. So if you're doing it and you've picked the wrong thing, switch it up, right? Like when we look at these 2 examples, well, this one's a little bit different. We look at this example, u is either x or u is e to the x. If we pick the wrong thing and it's not working, well, there's only one other option, flip it around. But these ones definitely work. Most of the things we'll do work following our formula. So our first one is the integral of x e to the x. Not a quotient. There is nothing that u sub is going to do to help you out. The only other option we have in AP Calc is to do integration by parts. And that is what's going to work here. So we've got to first identify our u. U is going to be, looking down the list, the first thing I see that I have is something algebraic. So my u is x. And my dv is the remainder of my integral. So we're going to say e to the x dx. And then we are going to take the derivative of u and we are going to integrate v. So the derivative of x is 1. So I'm going to write dx, yeah, just dx, yeah, dx, yep. And when I integrate e to the x dx, I get e to the x, yep. Cool. All right. And now I'm just going to follow my formula. If you write your, if you write your stuff out, it's always going to be the same pattern. The formula is that this integral equals uv outside of an integral. It equals x e to the x. Minus the integral of v du. So it's uv v du and if it's a simple example and you've done it right, that should be an integral that you know. We've already solved it once before. X e to the x minus the integral of e to the x is just e to the x. And now I don't have any more integrals, so I need to put a plus c. And again, it really just comes from the product rule. We integrated and we moved some stuff around from the product rule, so this absolutely has to work. Okay, example 3. There's a couple. When we started doing our must-know antiderivatives, they weren't just the functions; they were based on what we had gotten previous with derivatives. So we haven't seen this yet, right? We don't have a must-know integral for ln x. We have to figure it out. The thing with ln x is we know that 1 over x integrates to ln x. So what's our u? Our only choice is ln x, right? Yeah, that's it. But there still is a little bit more of our integral there, and that's dx. So dv is literally just dx. So you do have to take your entire integral and separate it. So now we will take the derivative on the left, integrate on the right. The derivative of ln x is just 1 over x. And the integral of dx would just be 1, but not 1, but it wouldn't just be 1. Sorry, I think I just agreed with you, but that was wrong. X, yeah. You're integrating 1 to get x. Yep. And this is why logarithm is such a good choice. You're going to see by the way that this all comes together now, why logarithm's always such a good choice to integrate by parts. I mean, really, we've taken a logarithmic function and gotten something algebraic. You know what I mean? We have 1 over x there. So uv, this integral is equal to u times v. So I'm going to write x ln x minus v du, but integrated. So that's going to be, I should have a dx here. I missed it. That's going to be x times 1 over x dx. I wanted to write that more in the middle. There we go. But x times 1 over x is just 1. In both of these examples, we've already done the integral already. We're repeating the integral. It's working out. So we end up with x ln x minus the integral of dx, which is just x. And we've integrated, so we get plus c. Cool. Not bad, right? Nope. Let's do it with some definite integrals. We just have to evaluate along the way. That uv is going to get evaluated at 0 to 4. Very similar, x e to the negative x. Algebraic versus exponential. You're going to pick the algebraic. This is almost exactly what we had earlier. U is x, du is dx, dv is e to the negative x dx. But in this case, v is going to be, when we integrate e to the negative x, negative e to the negative x. Yep. Cool. uv minus v du. So we've got x e to the negative x, and we've got to evaluate that from 0 to 4. Negative, yes. Yep, thank you. Negative x e to the negative x. Thank you. Yep. And then from that, we've got to subtract the integral of v du, but that's got a negative in it. So I'll make this positive. I swear not everyone just ends up repeating that same derivative. I didn't realize that. Even when I did these earlier too, and I didn't quite catch that. And that should have limits on it, 0 to 4. Cool. Alrighty. So we're going to end up, we're going to kind of evaluate, we've got kind of two different things to do here. The first one's ready to go to be evaluated. We have to integrate this one. We've already done that before. So it's going to be, as far as the evaluate part, it's going to be negative 4 e to the negative 4 minus 0 e to the negative 0, so just 0. Plus, we already integrated e to the negative x dx. It's negative e to the negative x dx. Just no dx, sorry. Minus e to the negative x. And that needs to be evaluated from 0 to 4. As I'm doing this, I'm thinking every time to make sure that I haven't missed like putting those evaluated ins. This is a number, so everything you have needs to come out to be a number. X e to the negative x isn't a number unless we evaluate it at something. This is a number because it's got limits. This isn't a number unless we evaluate it at something. So looks like we have negative 4 e to the negative 4 minus the quantity e to the negative 4 minus e to the 0, which is, of course, just 1. So not matching the answer I got this morning. I had negative 3 here. But did I miss a negative this morning, or did I miss something now? I think I missed it this morning. So we've got negative 4 minus 1, which is negative 5 e to the negative 4th plus 1. You guys didn't, nothing was jumping out at you as, wait, why did Cranac put that sign there, did you? Okay. I almost checked it too this morning, and I should have. That way I would have known. But yeah, I definitely had a 3 there in my notes, but we did have to flip the sign a few times there. The minus from the integration by parts formula became a plus because we were plugging a negative v in. We integrated, that gave us a negative here. I wonder if that's where I missed it. So we still have that negative. We plugged our 4 in first. Yeah. Yep. Okay. Cool. Right. Don't get in the habit of always picking the x as your u, because looking at example number 5, what comes, I mean, not that there's very many choices here. We've got x cubed and we've got ln x. We want the ln x. Logarithmic is the best choice in most cases as your first one. So we have ln x. We have 1 over x. So dv would be x cubed dx, which makes our v. Yep. You have to take a derivative and integrate something in one problem. So it looks like we get uv. So we have ln x times x to the 4th over 4. There's no good way to write that. Let's do this. X to the 4th ln x over 4. Evaluated from 1 to e, because why not? V du, x to the 4th over 4x, x cubed over 4. And with limits from 1 to e. It's not a number unless it has the limits. All right. Same process, not too bad. X to the 4th over 4 v du, because I multiplied by 1 over x. Yeah, I could have written it out, but I just said it. So we've got e to the 4th ln e over 4 minus 1 ln 1 over 4. 1 to the 4th, really, but ln1 is just 0. So yes, that guy's gone. This is 0. Minus x to the 4th over 16. Evaluated from 1 to e. Because why not? Thinking ahead a little bit here. This is going to give me e to the 4th over 16 minus 1/16, right? Which means that I want this. What this has an ln e is just 1. So I can cancel that off too. So that gives me e to the 4 over 4, but I want a denominator of 16. So I'm going to do that in line here and write this as 4 e to the 4th over 16. That could take you 1 or 2 extra steps, and there's nothing wrong with that. Maybe this is what I was thinking of the 3 from. Maybe I actually did get -5 over there this morning. So this time I am going to get that 3 that I remember from earlier. 4 e to the 4th over 16 minus 1 e to the 4th over 16 is going to give you 3 e to the 4th over 16 plus minus 1/16. Sound good? Okay. I think what I wanted to do when I looked at this morning, I definitely want to do number 6, and then we're going to skip over. There is a second, I don't want to say, yeah, there's a shortcut that you could take in certain problems. We'll skip over that and do that tomorrow. Yeah. Along with the double up. We'll see. Just thinking out loud. Definitely want to take a look at number 6. Again, like I said, with our antiderivatives, ln was sitting there. We didn't know how to integrate ln. Now we do. We don't know how to integrate arctan. We know how to get arctan by integrating, but we don't know how to integrate arctan. It actually works a lot like ln x, because if you look, it's just a function with the dx, so you don't have a lot of choice on what's your u and what's your dv. As long as this actually works out, as long as your vdu is a little bit easier to integrate, you're set. So we have the arctan of x here. We have dx here. Integrating dx just gives us x. And the derivative of arctan, 1 over 1 plus x squared, or vice versa, dx. You think this would work with, I didn't do it, but I think this would work very similarly with sine. I think your sine would work out very similar, not exactly the same because it's a different derivative. But watch what happens when we do this one. So we've got our uv, we get x arctan x minus the integral of v du. So that's going to be x over 1 plus x squared dx. What should I do with that? What's that? No, the bigger power needs to be in the numerator. What's that? U sub, yeah. The directions help figure that one out too. But yeah, that's U sub, because if you make U, what do we want to make U? 1 plus x squared, du is 2x, which is what we've got. We've got an x, so we're set there. Yep. When I did this in my work earlier, thinking pure FRQ reasons, I decided to call it U1, because I've already said that U equals arctan x. So in your scratch work on a multiple choice question, you're fine to just use a regular U. And honestly, even if this were an FRQ for me, I'd be okay with that. I feel like I'm taking an abundance of caution there by doing that. So my U1 is 1 plus x squared, which makes my du1 equal to 2x dx. But we don't have 2x dx, we just have 1x dx. So we want, what we really have here is 1/2 of du1. So that integral we have above still equals x arctan x. But now that's minus the integral of, or minus 1/2 the integral, because we have that 1/2 du that we're replacing our x dx with, of du over u. Again, in all these cases, I'm fine not putting a plus c anywhere because I haven't taken an integral yet. Now here's where we're going to get our plus c. So move this guy out of the way just so that it looks, that's not what I wanted at all. Yes, I do want to do that. Yes, good call, Austin. Yep, I do want to do that. Oh, I'm still in drawing a square mode, which is not what I want. That's why it's not giving me nice ones. Okay, yes, that's definitely what I wanted to do. Okay, so we do that, and I was trying to move these guys around a little bit, or even just shrink it up a little bit. There we go. Oop. Nope, lost him. There we go. Still there, just smaller. So this equals x arc tan x minus 1/2 VLN of the absolute value. I'm not going to write u. I'm going to write 1 plus x squared. And as a matter of fact, in my notes, I didn't even write the absolute value bars, because could 1 plus x squared be negative? Nope. Oh. Is your answer wrong if you leave those absolute value bars? No way. Plus c, thank you. Is your answer wrong if you forget the plus c? Absolutely. Is that plus c? Yeah. Good thing I left all that space at the bottom, right? I'm usually devoid of space. Okay. So the things that we are going to at least skip for now. Hey, what happens if you get an integral where that integral at the end is something that can't be solved unless you do integration by parts? So you actually have to do it twice. That's what's going to happen in example 7 when we do it tomorrow. It's what's going to happen in our last example today as well. But then we're going to learn a method for when we know that that's going to happen to do it a little bit simpler. So that's going to be a big positive. So we'll learn the DI method tomorrow. We're going to look at one last case here where something a little bit more interesting happens. We are going to have to integrate by parts twice, and we are actually never going to solve an integral when we do this problem. There's never going to be a point where we're going to solve an integral, because watch what happens here. I feel like this is only really going to happen when you're working with sine and cosine, because what happens with sine is you repetitively make your way back to where you were in the beginning. What's going to happen is we're going to do integration by parts twice, and we're going to have this function back. We're going to have it again. So we're actually going to have an equation that has this integral on both sides of it, and then we're just going to bring them all to the other side, and we'll have our answer. So let me show you how that works. LIATE, our u is going to be cosine x, which makes our v e to the x dx. Yes. Yep. Yeah, I had that nice sheet where the table was there for me. All through my notes, I kept doing this wrong too. Yeah, dv equals e to the x dx. Yep. That's going to put du here and v here. The derivative of cosine is negative sine. Yep, and then the dx, correct? And integrating e to the x, of course, just gives us e to the x. So integration by parts tells us that this integral is equal to cosine x e to the x minus v du. There's a negative sign, so plus the integral e to the x sine x. I don't really have a good order to be writing these in. I should stick with the original problem. I'll make this also say e to the x cosine x, for no other reason that I should pick something and stick with it. So put the exponential first, put the trig second. Okay. If we don't know how to solve e to the x cosine, if we can't just easily find a derivative of e to the x cosine x, we probably can't just easily find a derivative of e to the x sine x. So we'll do a second integration by parts. So we'll have a u1 and du1. I'm going to write these all out so I get them right for once. dv1 and v. And we are going to choose them the exact same way. This time u1 will be sine x, leaving dv to be e to the x dx, which still makes v1 e to the x. And then the derivative of sine is cosine. Yep. And then the dx. Cool. Okay. So our original integral still equals e to the x cosine x plus something. And that something is what I get when I integrate this integral by parts. So plus v1 u1, so e to the x sine x, minus the integral of v1 du1. So that is e to the x cosine x. So now here's what happens with this one. I have an equation. Some integral that we want to find is equal to e to the x cosine x plus e to the x sine x minus the integral that we want to find. I'll write it since I have all the room. E to the x cosine x dx. So I will add e to the x cosine x to both sides. So I have 2 times the integral of e to the x cosine x dx equals e to the x sine x plus e to the x cosine x. And I'll divide both sides by 2. And I haven't actually done an integral. I guess that's kind of a lie because I did integrate every time I went from dv to v. But there was never a part where in my line I had an integral that I solved. I just ended up algebraically figuring out that the integral of e to the x cosine x dx is e to the x sine x plus e to the x cosine x over 2. Make sense? It doesn't feel right. So that's just that, sure, right? I mean, everything's equal, so it has to be. But yeah. Cool. Bad. Yeah, plus C. Plus C. Yeah, plus C. Yeah. Yeah. That's why it didn't feel right, right? I said it didn't feel right because it didn't have its plus C. Yes, plus C. Absolutely. I need like a jar. Every time a student calls me out on plus C, I should drop a quarter in. Or I forget the dx in one of these pieces. Now I can't afford that. Cool. All right. So yeah, I'm pretty sure that the stuff that we haven't gone over, you don't need until the non-Mr. Bean page. So yeah, these ones are the ones that I've added where those things come into play. So definitely plenty of time to practice some of these. Or go back and do the other work.
Guess I should just wait and show you everything.
Okay, yeah, sure. Yeah, all right, we'll take it.